Welcome back everyone. In this video we'll be discussing the effect of temperature on solids. And to do that we'll be answering these two questions. But before we do that, let's look at some information that might be helpful. Solids expand and contract, with their change in length proportional to their length and change in temperature. This is neatly summarized in this mathematical formula where delta L represents the change in length. This Greek letter alpha represents the coefficient of linear thermal expansion, and depending on the material, this value, which is a constant, will change. And these values are provided in your textbook, and I've also provided them in a table underneath. L represents the length of the shape, its original length before the change, and delta T is the change in temperature. Over here I've just rearranged the formula so that the L is being divided by delta L. Now we can look at question number 1. A steel bridge is set on concrete pillars on opposite sides of a river. The bridge is 300 meters long, and the work is performed on a day when the temperature is 18 degrees. What clearance is required for the bridge not to buckle at 45 degrees Celsius? Let's do a quick illustration. These are the concrete pillars in which the steel bridge sits on. And that is the steel bridge. It spans 300 meters. And we want to know how much this bridge will expand when it's 45 degrees outside. Okay, using the formula that was prepared above, we're looking for delta L. Delta L is equal to an alpha value for steel being 13.2. 13.2 times 10 to the power of negative 6 per degrees Celsius. That's alpha. That gets multiplied to the length of the bridge being 300 meters. And subsequently the difference in temperature as delta T. So 45 minus 18 makes 27. 27 degrees Celsius. Using our calculator really quickly, we have 13.2 times 10 to the power of negative 6 times 300 times 27. That means that the bridge will expand by 0.106 meters. And to put that in perspective, that's 10.6 centimeters. So we need 10.6 centimeters of clearance to prevent this bridge from collapsing. Okay, let's move on to the next question. Firstly, how does temperature affect the volume of an object or the area of a flat object? When we're dealing with a flat object, it's important to note that the change in length is isotropic, meaning that it happens in all directions. Applying that to area and volume, the change in area is equal to 2 times alpha times the original area times delta T, and for volume it's delta V is equal to 3 times alpha times the original volume times delta T. So question 2 asks, calculate the change in volume of a brass sphere of 8.0 centimeters in radius on going from 0 degrees to 100 degrees. So here is our sphere, and I'll try to give it a 3D effect for you. And we want to know what the change in volume is from 0 to 100. Okay, let's use that formula. We have delta V is equal to 3 times, and the coefficient of linear thermal expansion for brass is 18.6. So 18.6 times 10 to the power of negative 6 per degrees Celsius times the original volume. Remember, to find the volume of a sphere, this is something that you should know, it is 4 over 3 pi r cubed. So we have been given the radius being 8.0, and you can leave that in centimeters, it doesn't really matter. So I have 4 over 3 pi 8.0 to the power of 3 times the change in temperature being 100 degrees Celsius. Okay, let's use our calculator. 3 times 18.6 times 10 to the power of negative 6 times 4 over 3 times pi times 8 to the power of 3 times 100. And that gives us roughly 11.96 or 12.0 centimeters cubed. To get a better perspective on that, if we were just to calculate the volume originally, okay, so back to our calculator, 4 over 3 times pi times 8.0 to the power of 3. So originally the volume is 2,144.6, and it has changed by 12.0 centimeters cubed. Essentially, it has expanded 12.0 centimeters cubed when going from 0 to 100 degrees Celsius. Pushing this idea further, if I were to compare 12.0 centimeters cubed to the original being whatever that was, and we found it to be 2144.7 centimeters cubed. If I were to divide this out, 12.0 divided by what I just found, and multiply that by 100, I would get a percentage difference of roughly 0.56%, expanding from 0 to 100 degrees Celsius. And there you have it. Now you know the effect of temperature on solids.